A reinforced concrete wall, 300 meters high, 50 meters thick, and stretching for 160 kilometers, suddenly appears in front of you. What does it make you think of? I understand why you might think that. But you are not standing on Paradise Island. You are on the vast plains of the central United States. And there is not just one wall. There are three. What they are meant to stop is not a giant, but something even larger and far more unpredictable: a tornado. In 2014, Rongja Ta, a professor of physics at Temple University in the United States, proposed building three giant walls across the central United States, each about 300 meters high. The walls would act as artificial mountain ranges, weakening the collision between air masses moving from the north and south, and in theory, reducing the likelihood of tornado formation. This was not the premise of a science fiction novel, nor was it the first time people had come up with an extraordinary idea for defending themselves against tornadoes. As early as the 19th century, people were already trying to influence the weather with cannons and explosives, hoping that shock waves could disturb clouds and produce rain. When it came to tornadoes, some began to wonder whether similar forces could be used to disrupt the storm itself. Over time, the proposals became increasingly ambitious, seeding thunderstorms with chemicals, using explosives to break apart rotating air, cooling warm, humid air with liquid nitrogen, or even placing fleets of enormous balloons in the path of an approaching tornado. Some of these ideas were tested on a small scale. Others never went beyond papers, patents, or imagination. But whether practical or not, every one of these seemingly wild proposals reflected how people of the time understood tornadoes. Today, we are going to explore a brief history of tornado defense, from storm cellars to a 300-meter wall. Tornadoes are not the largest natural disasters in terms of the area they affect. They do not stretch across hundreds of kilometers like hurricanes, nor do they leave entire cities underwater for long periods like floods. The damage path of a tornado may be only a few hundred meters wide. But within that narrow corridor, roofs can be torn away, cars can be thrown through the air, and pieces of wood, glass, and metal can become high-speed projectiles. For people living in the central United States, this is not a disaster that appears only occasionally in movies. On March 18, 1925, a tornado tore across Missouri, Illinois, and Indiana, leaving behind a trail of destruction hundreds of kilometers long. It killed 695 people, making it the deadliest single tornado disaster in United States history. At the time, there was no modern weather radar, no mobile phone warning system, and no numerical forecasting models capable of identifying high-risk areas in advance. Many residents did not realize the storm had arrived until they heard a deafening roar and saw pieces of houses being thrown into the sky. Faced with a disaster that often came with almost no warning, the most direct form of protection was to go underground. As a result, storm cellars gradually began appearing beside farms and homes across the central United States. On May 22, 2011, an EF5 tornado passed directly through the city of Joplin, Missouri. By then, the United States already had Doppler weather radar, live television weather coverage, outdoor warning sirens, and a relatively advanced warning system. Even so, the tornado killed 158 people, injured more than 1,000, and severely damaged large areas of homes, shops, schools, and hospitals. There were many reasons behind such a devastating loss of life. The tornado intensified rapidly and moved directly into a densely populated area. Some residents did not hear the warnings in time. Others had received tornado warnings many times in the past without ever seeing a tornado, so they did not immediately respond to this one.
Okay, there's no tornado. 9 times out of 10, it's a false alarm.
Many local buildings also lack basements or dedicated shelter spaces. But regardless of the problems with warnings, buildings, or human response, the most immediate cause of the disaster was still the extraordinary destructive power of the EF5 tornado itself. And every form of defense begins with understanding the storm. So before we explore the history of tornado defense, we first need to answer two basic questions. How does a tornado form? And why do these storms occur so frequently in the central United States?
Many people imagine tornado formation as a simple process. Cold air collides with warm air, and the atmosphere begins to rotate. But the real process is far more complicated. First, a large supply of warm, humid air is needed near the ground. When this air is lifted, it rises rapidly and helps create a powerful thunderstorm. At the same time, wind speed and direction vary at different altitudes. This vertical wind shear can cause the air to begin rotating along a roughly horizontal axis. When a strong updraft moves through this rotating air, it gradually tilts the rotation upward, turning it into a vertical column. Inside the thunderstorm, this can develop into a large rotating updraft known as a mesocyclone. A thunderstorm containing a mesocyclone is called a supercell. Many of the most destructive tornadoes come from these storms. But not every supercell produces a tornado. Only when warm, humid air near the ground, colder air, updrafts and downdrafts interact in a very specific way can the rotation tighten and extend toward the surface. It is important to note that even today, scientists still do not fully understand many of the details involved in the final formation of a tornado at ground level. What we can describe is still only a general outline. That is why two supercells that appear almost identical may behave very differently, with only one of them producing a tornado.
Now, from what I gather, west, we double our chances. East, well, it's high risk, high reward.
Two cells to the west are fighting over the same inflow. They'll choke each other out. This one to the east is the sky all to herself. Moisture, wind shear, instability.
Tornadoes are not unique to the United States, but in both frequency and intensity, the United States stands out more than any other country. Around 1,200 tornadoes are recorded in the United States each year, while only several hundred tornadoes over land are reported across the whole of Europe. European tornadoes are generally weaker, while violent tornadoes reaching EF4 or EF5 intensity or remaining on the ground over long distances are far more common in the United States. This difference is not accidental. The central United States regularly brings together the conditions needed for severe thunderstorms and tornado formation. Warm, humid air moves north from the Gulf of Mexico, while cold air pushes south from Canada. At the same time, the plateaus and deserts of the southwest continuously send in hot, dry air. These very different air masses meet over the vast Great Plains. Combined with the strong wind shear created by the jet stream high above, they create an environment highly favorable to the formation of supercells. The region stretching across northern Texas, Oklahoma, Kansas, Nebraska, and South Dakota is commonly known as Tornado Alley. But it is not a fixed corridor with clearly defined borders. What the name really describes is a vast region where the conditions for tornado formation occur repeatedly. As people gradually came to understand these processes, a new idea began to emerge. If tornadoes depend on specific patterns of airflow, temperature, and humidity, could changing just one of those conditions prevent a tornado from forming? From this point on, people were no longer satisfied with simply taking shelter or issuing warnings. They began trying to interfere with the storm itself.
When people first tried to defend themselves against tornadoes, their first instinct was not to study them. It was to open fire. In the 19th century, the mechanisms behind severe storms were still poorly understood. Some people in Europe and the United States believed that shock waves from artillery or shells exploding in the air could disperse storm clouds, prevent hail, or even alter a storm. So when dangerous weather approached, people sometimes fired cannons into the sky. By the end of the 19th century, the United States had even carried out much larger experiments using explosions to modify the weather. In 1891, in a drought-stricken region of Texas, Robert St. George Dyrenforth led a team that attacked the sky with explosives, mortars, and balloons carrying explosive charges, hoping to shake the clouds and produce rain. The experiment failed, but it left behind an idea. Perhaps a sufficiently powerful external force could disrupt the airflow inside a storm and influence a tornado. That idea would return again and again in new forms. By the middle of the 20th century, cloud seeding technology began to attract serious attention. Using aircraft or artillery, people released substances such as dry ice and silver iodide into clouds, hoping to alter the formation of water droplets and ice crystals. This led to a more ambitious idea. Could chemicals be released into a thunderstorm capable of producing tornadoes, forcing moisture to condense and fall earlier and thereby reducing the storm's energy? But a tornado is not an isolated mass of air. Inside the supercell, updrafts, downdrafts, precipitation, and rotation all interact at the same time. Increasing rainfall would not necessarily weaken the storm. It could also alter cold air outflows and airflow boundaries, producing unpredictable results. For this reason, cloud seeding never became a reliable method of tornado control. Others proposed creating airflow that rotated in the opposite direction, using an artificial vortex to cancel out the tornado. Some patents suggested placing giant fans or rotating machines along a tornado's expected path, continuously forcing counter-rotating air into the storm in an attempt to disrupt its structure. The idea sounds simple, but a real tornado operates on an enormous scale, and the airflow produced by any machine would be tiny by comparison. Even if such a device could disturb the funnel near the ground, it could not cut off the energy continuously supplied by the thunderstorm above. A British patent published in 1999 proposed detonating explosives near a tornado, using shock waves to disrupt the high and low pressure regions inside it. Other similar ideas included injecting fuel into the rotating airflow, waiting for it to mix with the surrounding air, and then igniting it. Another proposal involved launching explosive rockets into the tornado, allowing them to rise inside the circulation and detonate repeatedly at different altitudes. All of these concepts can be seen as modern extensions of 19th century cannon fire, but the problem remained the same. Even if an explosion temporarily disrupted the funnel near the ground, the supercell producing the tornado would still be there. As long as warm, humid air and rotating updrafts continued to feed the storm, the tornado could form again. The explosions themselves would also create shock waves, fires, and large amounts of debris. In trying to stop one disaster, people might simply create another. In 2008, American inventor Stephen Cummings proposed another approach. Large aircraft or drones could release liquid nitrogen into the air near a tornado. Liquid nitrogen has a temperature of nearly -196 degrees Celsius. As it vaporizes, it absorbs a large amount of heat. In theory, this could cool the warm, humid air near the ground and disrupt the conditions needed for the tornado to continue developing. The idea later received a United States patent. Other designs went even further, proposing that liquid nitrogen be packed into bomb-like containers and delivered by transport aircraft, bombers, or cruise missiles. But this concept faced the same problem of scale.
A small amount of liquid nitrogen could cool only a limited volume of air, while a supercell continuously draws in enormous quantities of warm, humid air. To influence the entire storm, the amount required would be far beyond what aircraft could carry, and approaching a tornado at low altitude would itself be an extremely dangerous mission. When explosives, chemicals, and liquid nitrogen all appeared unlikely to work, some people shifted their attention away from the tornado itself and toward the geography that helps produce it. This brings us back to the giant wall proposal mentioned at the beginning of the video. In 2014, Rongjia Tao, a professor of physics at Temple University, proposed building 3 enormous east-to-west walls across the central United States. Each wall would be around 300 meters high and 50 meters wide. One would stand in North Dakota, another near the border between Kansas and Oklahoma, and the third across southern Texas and toward Louisiana. These walls were not intended to stop tornadoes that had already formed. Tao argued that the central United States lacks major east-to-west mountain ranges, allowing air masses from the north and south to travel long distances before colliding. If giant walls could imitate low mountain ranges and slow these airflows, perhaps they could reduce the chance of tornado formation at its source. According to some reports, each wall could extend for 160 kilometers and cost more than $16 billion.
Meteorologists quickly pointed out that although 300 meters is extremely high for a building, it is far too low compared with a supercell that can rise more than 10 kilometers into the atmosphere. Air could simply pass over the top of the wall. It might also be forced upward in front of it, and rising air is itself one of the key ingredients in the formation of severe thunderstorms. Later numerical simulations also suggested that walls of this size would not prevent powerful supercells from forming. At most, they might shift where storms appeared rather than make them disappear. The walls were never built, but the idea of physically blocking a tornado did not disappear. In 2020, Chang Ye, a researcher at Lawrence Berkeley National Laboratory, proposed using large numbers of interconnected giant balloons to form a temporary barrier in the sky. The balloons would be deployed across a region where a tornado might pass, increasing air resistance and interfering with convection in an attempt to reduce wind speed and rotation. It could be seen as a lighter and more flexible version of the giant wall proposal. But the exact path of a tornado is extremely difficult to predict, and the balloons and their cables might not survive powerful winds, hail, and flying debris. The 2024 film Twisters brought the dream of taming a tornado back to the screen. The production also consulted scientists from the National Severe Storms Laboratory, part of the United States National Oceanic and Atmospheric Administration, or NOAA. In the film, the main characters first seed the storm with silver iodine, then release large quantities of water-absorbing polymer, hoping to make moisture condense and fall rapidly to the ground until the tornado collapses. Like many of the ideas discussed earlier, the concept contains a certain scientific logic, but would be extremely difficult to make work in reality. A tornado would not stop simply because moisture was removed from its funnel. The funnel is only the small part of a much larger supercell that becomes visible near the ground. What truly sustains the tornado is a thunderstorm system operating across tens of kilometers. From 19th century cannons to explosives, liquid nitrogen, giant walls, and balloons, the proposed solutions became increasingly complex. But even today, humanity has still not found a reliable way to prevent a tornado from forming or to make one safely disappear after it has begun. Another technological approach, however, has achieved real success. If we cannot stop a tornado, then the next best option is to know where it will appear as early as possible. Humanity still cannot prevent tornadoes from forming, but we can now detect the danger much earlier than before. The first step in modern tornado defense is to identify which regions may develop severe thunderstorms before the storms appear. Meteorologists analyze temperature, humidity,
atmospheric instability, and changes in wind speed and direction at different altitudes. When conditions become dangerous, severe weather outlooks can be issued in advance. By the middle of the 20th century, radar had gradually become part of weather observation. Early weather radar mainly detected precipitation. Meteorologists looked for distinctive patterns, such as hook echoes, that could suggest rotation inside a storm. Later, Doppler radar made it possible to measure whether raindrops are moving toward the radar or away from it. When neighboring areas show high-speed movement in opposite directions, it may indicate rapid rotation. In 1973, researchers used experimental Doppler radar to record the full development of the Union City tornado in Oklahoma. For the first time, people could see the rotation inside a storm through the clouds. But radar still cannot determine with certainty whether a supercell will actually produce a tornado. That is why modern warning systems also rely on reports from trained spotters, police officers, firefighters, storm-chasing teams, and ordinary residents. Once the danger has been detected, the next challenge is to deliver the warning to everyone in its path as quickly as possible. From early telephone calls, radio broadcasts, and messages delivered by hand, to television, mobile phones, and wireless emergency alerts today, warnings have become faster and more precise. Modern tornado warnings often provide only 10 to 15 minutes of lead time. That may not sound like much, but it can be enough for schools to stop activities, shops to evacuate customers, families to enter basements, and hospitals and fire departments to activate emergency procedures. But receiving a warning is only the beginning of tornado defense. What often determines whether someone survives is whether there is a safe place to shelter after the warning sounds. The earliest storm cellars were usually built beside homes and farms. Later, people began constructing safe rooms inside buildings, using reinforced concrete and impact-resistant materials to protect those inside. The buildings themselves could also be strengthened. Connections between roofs, walls, and foundations could be reinforced, while doors, windows, and exterior walls could be designed to better resist powerful winds and flying debris. These measures cannot leave a house completely unharmed in the strongest tornadoes, but they can slow structural failure and give residents more time. From risk forecasts and radar tracking to warning systems and safe shelters, humanity has gradually built a complete line of defense. Our real success has not been controlling the storm itself, it has been delivering information faster, acting earlier, and helping buildings survive for longer.
To make a tornado disappear, humanity would have to change far more than the funnel in front of us. Even if that funnel is several hundred meters wide, it is only the most violent part of a much larger thunderstorm system, reaching down toward the ground. What would truly need to be altered is an entire atmospheric structure extending more than 10 kilometers into the sky and stretching across tens of kilometers. Even today, we do not have that ability. The 300-meter walls proposed in 2014 were never built across the central United States. They were too expensive and too enormous. More importantly, they could not truly stop tornadoes. But through radar, communication, and engineering, humanity has built another kind of wall, one far more realistic. From the earliest storm cellars to radar, warning sirens, mobile alerts, and reinforced concrete safe rooms, an invisible line of defense has gradually taken shape. It has increased the speed at which information travels, strengthened buildings against destruction, and changed the way people respond to disasters. This wall cannot be seen, and it cannot stop a tornado,
but it can leave more people alive after the storm has passed. This is BHE, Brief History of Everything.